All right. Okay, so let me recap what we were talking about yesterday. Okay, so we were talking about how a cell can extract information about the molecules in the surrounding medium by looking at the occupation of a receptor on its surface, right? So we have this picture of E. coli. It has some kind of surface molecule that has a little pocket that allows it to grab onto small molecules, presumably, that are floating about in the medium. And every now and then one of them gets trapped on this little receptor, and that causes something to happen inside, all right? So the information available to the cell is, as a function of time, is this receptor occupied or not, right? So we have some kind of, here's the occupation as a function of time. It's a series of ones and zeros. It's that sort of thing, okay? It's either got a molecule sitting in the pocket or not, and that changes with time. Okay, and let's see, so sort of the very first thing that you might be interested in is what's the average occupation number, all right? And the average occupation number is related to the concentration of the molecules outside. All right, so we work through the kinetics of that. That is to say, when on average over long periods of time, the rate at which the receptor goes from occupied to unoccupied has to be equal to the rate at which it goes from unoccupied to occupied, right? Otherwise, you have a buildup of probability. So this allowed us to say that the average occupation was equal to the concentration outside divided by the concentration inside plus this number what did we have? Tau B. Okay, where D is the diffusion constant that characterizes the molecule that's diffusing around outside. This S is a dimension because we modeled, for purposes of argument, we modeled this receptor as simply being a little disk that has some radius S. And the bigger the disk, presumably, the more likely it is that a molecule is going to hit it. And we modeled if the molecule hits the disk, then that's it, right? It's bound. Okay, so, and then we did the diffusion calculation to find out what is the rate at which molecules diffuse out of solution and hit this disk. And we found that it was basically this diffusion constant times S. Now, there's a time involved, and that is the time on average that the molecule stays bound. So if you have a receptor that's got a molecule sitting in it, then if you wait long enough, it's going to come off, right? And then there's an average time for it to come off, or the rate for it to come off is 1 over some characteristic time. And that's what this guy is. And this characteristic time is related to the binding energy of the molecule when it goes out of solution and gets stuck to this receptor, all right? Now, I will, at some point soon, talk about how you connect this binding, this average residence time to the binding energy. That's the little statistical mechanical calculation, but let's leave that aside for the moment. So this might be called C half or C50 or something like that. The point being that this number, which we can calculate if we know all of these things, is the concentration at which the occupation probability is 50%. All right? Okay, so this is a standard sort of chemistry, how shall I put it, chemical kinetics formula. And it tells us, if we know the average occupation probability of the receptor, you can read off what the concentration outside is. And so let's see, what are we going to do? We're going to say we have a, yeah, so we can rewrite this formula as telling us that for ds tau b times c is equal to average p over 1 minus average p. All right, so if the cell measures this average occupation number, it can put the number into this formula and get out an answer for what's the concentration outside. Okay, so that's the general idea. So what are we going to do with this? Okay, so what do I mean by the average concentration? Well, I must mean the average taken over some time span. All right? So what I really mean is the integral over time of the occupation state over some time t, averaged over that time. All right? So this occupation number is going from 0 to 1. It's flickering. Sometimes it's 0, sometimes it's 1. And what I can do is, what I'd really like to know is what is the average over all time, right? But I can't do that. I have to make a measurement over a finite time. So I have to average what's happening over some time interval, all right? Because I'm doing an average over a finite time interval, the answer I get is itself going to have some fluctuations. And that's the thing I want to get a handle on. So this guy will fluctuate. Not as rapidly as the occupation or the instantaneous occupation number, but it's, you know, it's a noise problem. I'm trying to get a signal out of noise, and the best way to do it is to average, and the longer I average, the better, the more accurate an estimate I get. And what I want to do is today I'd like to know or estimate or calculate what is the variance in this guy. Okay, so what I'd like to get a handle on is, let's see, how do I want to do this? I want to say, if I take my measurement and I know that I'm not going to get exactly I'm not going to get the true answer exactly. I'll get something that differs from it, presumably by less and less as I make the time over which I average longer and longer. But I'd like to get a measure of this guy. So average this, and let's just call that delta p average squared or something like that. If this guy is, so this is a measure of the error that I'm making in measuring the average occupation number, and that's going to be telling me what is the error that I'm making in determining what is the concentration outside. Right? So what I want to get a hold of is this guy. All right? So delta p over, there's going to be some relation between the error I make in measuring c, the fractional error that I make, is somehow going to be related to the fractional error that I'm making in measuring the occupation number. I put a twiddle there because there's some factors, but roughly speaking, okay? Okay, so this is what I want to focus on. How do you measure this? All right, so let's have a look at that. This is coming down to a, all right, so, you know, I have a definition of what I mean by the average occupation number over some time interval capital T, and I want to square it. Let's see, so, okay, yes, I could have taken one more step and probably should have, namely, what I really want here yeah, so this is going to be in the usual fashion the average of the square of this guy minus the square of the average. Okay? Minus p bar squared. Let's just call it this. Okay, so when you do a variance of a calculation like this, the cross terms cancel, well, the cross terms cancel out, or the cross terms can be absorbed. And what we're really looking at is what is the mean square of the thing that I'm measuring minus the square of the mean of the thing that I'm measuring. That's what I'm after. So what I want to calculate now is what is this mean square?
Professor?
Okay.
Professor?
Yes.
Excuse me. Could you clarify again what's the difference between the p bar and the p bar with the index t?
Sorry. Okay, so if I average over all time, you know, take an infinite time interval, I'm going to get the true average, all right? Now, my problem is that I can't average over all time. I have to do things in some time window, and well, I'll explain in more detail what it is that sets that window. But if I discover that, you know, in order to get enough accuracy in measuring the concentration, I have to wait for a year, okay, this is going to be a problem. So the bacteria have to do things on this time scale of seconds, right? Maybe a minute, who knows? But, you know, if I get an answer of a year, then I'm in trouble, all right? Okay, so my issue is somehow quantifying what's the difference between the true average, you know, averaging for over all time, and the actual approximate average that I can have access to. That's my problem, okay? And so analytically, what it boils down to is you have to measure this. Or rather, I now want to analyze this because the thing that I'm interested in, the variance in this measurement of the average, maybe I should have put a t here, is primarily determined by the average of the square of this thing. Okay, so now I'm interested in correlations is the problem. Okay, so let's just be totally clear here. Well, all right, so this is, what is this? This is 1 over t squared. Okay, so I'm going through a long argument, and I'll try to parse it into pieces that maybe it's best to think about them peacefully for half an hour away from the classroom. But I'll try to sort of highlight the various steps in the procedure. Okay, so I've got to integrate dt prime, p of t prime. Okay, and now I'm going to be averaging that. Okay, all right, so somewhere I have to learn about the average of a product of the occupation number at one time and the occupation number at another time. Now, it's pretty obvious that there's something called time translation invariance. So, or I can, okay, so let's rewrite this a little bit. Let's say that what I'm going to focus on is the average of p at some time and the average of p at some little time later that I'm going to count by tau, all right? Now, a very important semi-obvious fact, right, is that if you're averaging over t, unless something very strange is going on, this is just going to be a function of the displacement tau, all right? This is whatever is going on has time translation invariance. Nothing is changing as time goes on. So this kind of average can really only depend upon how far apart are the two measurements that you're making. Yeah?
Hey, can you explain the first equation? What is being integrated?
Okay, so I'm just
there?
taking this. Okay, here we go. Just 1 second. Where's the eraser? Here's the eraser. Let's do it. Okay. Okay, so literally, what I've got is P of t. That's one factor. That's the second factor.
What
Okay.
is the prime? Is that
Well, these
T
are
prime.
two independent calculations, all right? So this is the same thing. This is one way of writing the average over some time interval capital T, and so is this. Sorry about that. Okay, so when I'm doing the T is just an integration variable. It's a dummy, all right? But since I'm putting two of these two guys together, I have to distinguish between these two times. So I put a prime on it to say that this is just a different integration variable. Okay? Then I put it all together, right? And I get 1 over t squared. And then I have two integrals, an integral over dt, an integral over dt prime, and then p of t prime, da 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 da, okay? And now I'm going to make use of this, that when I'm taking the average, the only thing that matters is the difference between these two times, right? So, here's the thing. Here's t this way and t prime that way. And I'm integrating over this square to do this integral, okay? But in fact, the thing that I'm integrating really only cares about how far apart these two guys are. So I can simplify the integral quite a lot. So the goal here is going to be to calculate this guy, all right? Once I have this guy, I can, let's see. If I change, so if I change variables and I integrate that way and that way instead of that way and that way, okay, perfectly okay. Integrating this way, nothing happens. All right, so that gives me a factor of t. Integrating this way, I'm integrating over the time difference between these guys, so something does happen, all right? So when I'm all done here, let's put it this way, okay, so I'm going to have pt squared average. Well, integrating, so to say, in the diagonal direction will give me a factor of capital T. Nothing changes as I integrate along that way. So that'll get rid of one of those guys. And then I get to integrate over tau. But what I'm integrating is this correlation between the occupation number at two times that are separated by this amount tau. So I'm going to be integrating this. Okay, and this is a big number, so it's like integrating over infinity. All right, so this is what my problem is going to be. In order to get this fellow, which I'm interested in, this is the thing that measures the statistical error that I'm making, I need to calculate this guy, and I will be able to calculate it once I know this guy. What is this g of tau? What's this correlation? All right, so, okay, this is Okay. All right. So okay. All right. So there's an argument that I think probably I'm best advised to essentially describe the kind of arguments that go into it that'll tell me what is this guy. All right, so I'll tell you what the answer is, and then we'll talk about how you get that answer. So the answer is going to be that this guy, g of tau, I should say the t, is p squared plus p times 1 minus p e to the minus tau divided by 1 minus p is tau b. All right, so this is a fairly sophisticated and surprising looking formula. Let's just understand some things about it. So if the separation between these 2 points, this tau, is big, what do you expect? Well, if the separation between these guys is big, then there's really no correlation between what this fellow is and what this fellow is, and therefore it should reduce to the product of the expectation of each of these fellows independently. And that's exactly what this formula says, right? Because if I make the separation big, then this term dies, leaving this term, which is exactly what we were arguing. Now what about, okay, so, and this term says there's a time scale over which the correlation between what's the occupation here and what's the occupation at some time later, that correlation dies away on some time scale. Not surprisingly, the time scale is set by this rate at which the occupied receptor becomes unoccupied, this tau b, all right? Now, what about this funny factor p bar 1 minus p bar in front? That says that this correlation vanishes in 2 limits. One, the limit where p bar is 0, the other, the limit where p bar is 1, okay? Now, you know, if the concentration is very low, then p bar is 0. If the concentration is very high, p bar is 1. And if the concentration, you know, so if p bar is always 0, then, you know, the correlation between what it is at 2 different times just has no variation. It's just fixed. Likewise, if it's 1, if the p bar is 1, there's no fluctuation. So this correlation term has got to vanish when the occupation number is either 0 or 1 because you've made the concentration either very small or very big. Okay, now what we're really going to do is to take this, so if we put this into this formula, what do we get? Why don't I just carry that out to conclusion? All right, I'll go back in a minute and I'll tell you how it is you get this funny looking formula, right? It's sort of magical, actually. It's quite fun to carry it through. But once you've got it, okay, you are in a position to carry out this integral and find out what is the expectation of pt squared, okay? And that's the thing that's going to go down here to tell you what's the mean square error that you're making, okay? So let's do the integral, assuming the answer, and we'll come back to, well, how the heck do you compute this answer? Okay, so I just erased the integration that you do, but I think you remember, you can you can reorganize the integration variables so that you integrate over the average between t and t prime and the difference, all right? So the integration over the average gave us just a factor of t. Nothing is happening as you, that is, everything is independent of where you are in time. It's time translation invariant. So you have to do this integration over, this is tau, just to make sure that the difference between the two times, all right? Actually, I guess I'm integrating over that from minus t to plus t, if I'm integrating over this square. So there are two terms, right? There's the term that I get from integrating this piece, and that's just going to give me p bar, sorry, that's going to give me p bar squared, and then there's the term that comes from integrating over this piece, and doing it with, you can, of course, do it because you're just integrating an exponential, and when you do it, what do you get? I have it here somewhere. Integration. Okay. And now, okay, right. I get 2 tau b over t times p bar 1 minus p bar squared. All right, so there's one of these integrations is integrating over a constant, and I'm going to get something that's proportional, that is equal to the, is proportional to the total time available, and that's going to cancel this 1 over t. So that's going to give me a constant term. And then there's a term that doesn't give me something that grows with the length of the integration, and that's this term, and the 1 over t stays, all right? And that's important because that's going to tell us that the variance that's our problem is going to get smaller and smaller as I make the integration interval longer and longer, and that makes sense, right? The more data I have, the more accurate my answer. Okay, so
Professor?
actually,
Oh,
yes,
sorry.
go ahead.
I got a bit confused, and now I saw why I was confused. So perhaps if you could put the angled brackets in the second expression up there. I don't know if someone may be confused with that. The average of pt squared is equal to the average of those two integrals being multiplied.
Yes.
The term on the left,
Right,
it's missing.
We're up here.
Yeah, there I think it's fine. The left one, the
Okay.
one. Oh no,
No?
sorry.
Well, let me just make sure it's perfectly clear.
I think in the term is still there, which you haven't erased. There should be the angled brackets to mean it's the average of the product of those two integrals.
That's right.
And it's silly, but I just got confused. So in the left hand side, aren't there missing the angled brackets?
Isn't which mechanism?
The
Oh, here. Yes.
Yes.
Yeah, absolutely. I'm sorry. You're quite right.
Perfect. Sorry.
That's it?
Yes, just
All right.
that.
Okay. Okay, so this is a long song and dance to get us to a simple answer in the end. So, and the simple answer is pt squared minus, you know, the true answer, right, if you integrate forever. This is the variance. This is the thing that's going to be our problem. And so, when I subtract this constant term from our calculation, this guy goes away, and I'm simply left with this, all right? So this is going to be 2 tau b over capital T times p bar 1 minus p bar squared. Okay, so this is delta p, well, let's call it delta pt squared. Okay? And so this variance gets smaller and smaller as the time that you integrate over gets longer and longer. It's also small either if p bar is 0 or if p bar is 1. But that's because if the receptor is always occupied or never occupied, then there's no variation to worry about, but you're also not learning anything. So you're in trouble, okay? So the one thing that, so cleverness is required to get that, all right? Now, okay, let me just proceed to the, so to say, instructive end of the line, and then maybe we'll go back and explain, roughly speaking, how the cleverness works, okay? Okay, so fine. So now I know what this delta p squared thing is. What good does that do me? Well, I have a formula. So here we go, average. So I'm reorganizing this lecture as I go. That's why sometimes I stumble in the middle. Okay, now what do I want to do with this? Well, as I say, what I'm concerned about is what is the fractional error that I'm likely to make in my measure of the concentration. Okay, so I have an expression here for the concentration in terms of p bar. And you know what? This is actually 1 over c half. Okay? So maybe the right way to make this, to say this, is that all right, so let's rewrite all of this in a slightly more convenient form. So my best measurement divided by c half is going to be p bar as measured, my best measurement of p bar divided by 1 minus that. Okay? So it's sort of simple. There are these funny factors of p of 1 over 1 minus p, but in any case, there's the connection between the average occupancy and the concentration is pretty simple, all right? So if I make a mistake, if this guy fluctuates, if this measured thing fluctuates, as it will, right? We've just gone through the argument of what do you have to, you know, can you quantify how much it fluctuates? Okay, so then I can tell you that, so what I'm going to do is suppose I make a small change in this number, the thing that I've measured as the average occupation number over my time interval. Okay. Well, all I have to do is differentiate this with respect to PT, right? In other words, by how much does this right-hand side change if I replace PT by PT plus delta PT, okay? Because my measurements of PT are going to have some, if I do the measurement over and over and over and again, it'll have an average value, all right, there'll be some mean, but each individual value, each individual measurement is going to be fluctuating about. And that means each individual measurement of the mean occupation, as it fluctuates, it's going to cause my estimate of what is the concentration outside to fluctuate, okay? So just doing this little delta exercise, I find that this is delta PT divided by PT 1 minus PT. So I just take this and replace PT by PT plus delta and subtract, you know, the starting value, basically take the derivative, and this is what I get. Just put the two terms together. Okay, and I have my answer for delta. So delta PT is going to be something whose value is roughly that, right? That's what I've just calculated, the mean square variance in the thing that I measure. So I get to replace delta PT by whatever this other fellow was, P bar 1 minus P bar squared times 2 tau divided by T, and of course I'm dividing it by PT. I'm making the notation unnecessarily complicated. All right? You see where this part is just lifted directly from my computation over here, and this part is just from figuring out how does my estimate of the concentration change if I make a small change in my measurement of the mean occupation number. And that gives me the 1 over P times 1 minus P. So there's a lot of stuff cancels out, right? That cancels, that turns into that. And so I get 1 minus PT times 2 tau B over T. That's the error. So, wait a minute, sorry about that. I'm sorry, so this is delta PT squared. But, okay, so now I'm interested in delta PT, so actually, sorry, I think I have done this wrong. Delta PT. Okay, so what I really want to do is this. Okay. Okay, the thing I calculated for you is delta PT squared. Okay? So I have to square in order to get something that is directly usable. So this is going to be delta PT squared. So this all boils down in the end to 2 tau B over T times 1 over P bar. Okay, that is correct. Okay, and therefore, the thing that I'm kind of interested in qualitative terms, namely, what's the variance divided by half. Oh, I'm sorry. Okay, excuse me. All right, look. Okay, I haven't done this in front of a crowd for a while. Okay, so what are we really trying to do here? I have the delta CT divided by C half is equal to delta PT divided by PT 1 minus PT. That is correct. Okay. Now, what do I care about? Well, I care about delta CT divided by CT. Sorry, I care about, this is what's actually out there, and I care about the ratio between the mistake that I'm making and what's out there. What's the fractional error in the thing that I really care about, the concentration outside? Yeah.
To me, it's not clear why this identity holds, right? This delta PT divided by PT 1 minus PT. Where does that come from?
Oh, all right. So if I vary this guy, so I have this, so what I would like to do is to take this tells me that my inferred value of the concentration is determined by my measured value of the occupation fraction. Okay? Now suppose I make a small change. So I have a function of x, and I make a small change in the function. What is that? Okay? All right, that's exactly what I've done here. I've said, take this guy and ask by how much it changes if this guy changes a little bit. So I differentiate this with respect to PT and multiply the result by delta PT. That's this, all right? So, you know, differentiating, if I differentiate P over 1 minus P with respect to P, what do I get? 1 over 1 minus P plus P over 1 minus P squared. And if I combine terms, I get 1 over 1 minus P squared. So maybe I mean here DDP is 1 over 1 minus P, P over 1 minus P squared, that's 1 over 1 minus P squared. Okay. So, right. So this is, okay. So literally, sorry about that, this is now 1 minus PT squared, okay? However, what I'm really interested in is this, not the variance of what I infer compared to C half, but compared to CT. So what I really want to do is to take this and divide it by that. And that's how I get delta PT divided by P 1 minus P, okay? All right? Okay, good. This feels complicated, and it is complicated, and you know, you'll have to go back and sort of walk your way through it to convince yourself. But the end result is really very profound and deep, so it's perhaps worth once, not twice, but once, going through it in detail, okay? All right, so I think we're gradually getting everything together. Right, so this is just making use of this basic relation and asking how does the left side change if I change the right side by a little bit, and then say, what is it that I'm really interested in? I'm really interested in the fractional error or change in my inferred value of the concentration outside. That's what the cell cares about. Is there a lot of stuff to eat or not enough? Okay, and now if we'll just square it, we'll get something that we can carry over from our really clever argument that hasn't actually been explained to you just yet because it takes too many lines. And I wanted to make sure we knew where we were going before we got into the details of the clever argument. Okay, so delta CT over CT. This is the square of the error. Okay, so now we put all of that stuff together, and when we put this in, miraculously, what do I find? I find, okay, so this is now, as we'd said, it's this, and if we put in all of those funny numbers, what we get finally, that this is 2 TB over capital T times 1 over P bar. All right, so this fractional error, excuse me, the fractional error at least goes down as I measure, as I make my measurement window in time larger and larger. That's good. It just goes down like 1 over that time. Okay, so now we'll play one perhaps further little game with this. What we really want for purposes of estimation is not the square of this guy, but the guy itself. So I take the square root. And then with one slight further manipulation, I say this is equal to 1 over square root of. Now remember, there was a steady state relationship that defined what this off rate or off time was, right? So the average occupation probability times 1 over the off time times the off rate, this tau b, right, had to be equal to the on rate. That is to say, what was the number? It was 4 dsc times 1 minus p. All right, so this basically is just the rate at which particles are coming in from the solution to the receptor, right? Remember, this involves diffusion. What determines how rapidly stuff can arrive at the receptor is the concentration and the diffusion constant. Okay, so this is, I might call it 1 over T on or something like that. All right. It's the rate at which stuff comes out of solution and interrogates the receptor to know if it can be bound. All right. So we can re-express all of this actually as let's put the square root of 2 up top. 4 dsc times 1 minus p. Okay, so this is the fractional error. Times t, excuse me. All right, so we'll actually put some numbers in to figure out what this really implies for the life of a bacterium. But the point is, there's a very explicit formula for what is the mean, what's the fractional error that you're going to make if your only way of accessing the concentration of the molecules that are outside the cell is the occupation of the receptor as a function of time. 0, 1, 1, 1, 0, 0, et cetera, et cetera, et cetera. And so the cute further thing is, what is this number that's in the square root? Well, this part is just the rate at which molecules are coming out of solution and hitting the receptor, okay? The number that can actually be bound is going to be that, or the rate at which things bind to the receptor is going to be that rate at which they come out of solution times the probability that the receptor is open to receiving them, all right? So 1 minus p bar is the fraction of time that the receptor is unoccupied. So this whole thing in the denominator is, on average, how many molecules came out of solution and were bound by the receptor during the time that you were doing the measurement, okay? So basically, this fractional error is something that makes total sense from standard statistics. It's 1 over square root of n, and the only question was, what n, all right? And so the n was the number of times a molecule came out of solution and was bound by the receptor. So at the end of all of this, we get a really very simple answer, one that doesn't sound very surprising, okay, or whatever. But okay, there it is. And when you put in actual numbers, diffusion constants, sizes, typical concentrations, we'll learn some important things about bacterial life. Is there a question? Okay, so this was a little bit of a random walk. Sorry for that, but I think we got to the right place. Okay, so what we're going to do, we're going to exploit this. So let's all right, so we'll just remember mostly this. Okay, and so this is a funny looking formula, and the first time I started looking, when I first saw it and started thinking about it, it seemed quite odd. What the heck is this? Why is there this 1 minus occupation probability, et cetera, et cetera? But in the end, it makes total sense, right? It's just the total number of, it's just how many times you got a new piece of information. Something came out of the solution and got bound. And the longer you integrate, the longer you do the measurement, the more events of this kind happen. And good old Gaussian statistics tell you that the fractional error in what is, well, I mean, you had to really convince yourself that the translation from your estimate of the concentration to how many guys came on board is such that when you're all done, the answer you get really is exactly what you would expect from standard Gaussian sort of statistics. Not Gaussian, but it's more Poisson. Okay, so what I want to do is to draw consequences of this, but maybe I'll take 10 minutes to explain how this formula was derived. I think it is interesting. Okay, so let's, and it's also a bit miraculous. All right, so we're going for, at this stage in the calculation, over 1 minus p tau b. All right, so this is where we're at. Okay, so I'll summarize, I'll tell you the strategy. I'm not sure I will have the courage to do all of the details, okay? But anyway, oh, by the way, so on the, how do we do this? Okay. Okay, so now I have to do something, okay? No? Oh, it's right there. Okay, good. All right, so on the Dropbox, there's some information. So rough outline of the lectures. Okay, I finally figured out what I think I'll have time to do. You can look at it, but so for today, whoops, okay, good. Oh, that's all right, that's all right. Right, so for the first topic, there's some references. Okay, so what I'm talking about today is what's in this Berg and Purcell paper. This is one of, it's a kind of landmark in, how shall I put it, biophysics, physics and biology working together. This Physics of Chemoreception Biophysical Journal from 1977. Okay, so how do these guys propose to prove this? All right, taking my courage in my two hands, I tell you what it is. Okay, so we have some such time series. Yes, no, yes, no, yes, no. All right, so now take a pair of points that are separated by this distance tau. All right, I want to study the correlation between what's happening at a time and what's happening at a time that's later by tau. So that's a pair of points that are separated by tau. Here's another pair of points that are separated by tau, et cetera, okay? So these are different pairs of points. So take n such pairs. Just walk through the data and randomly choose a point, and then its distance, its time tau follower, and just do that over and over again. It doesn't matter. Just collect n such points. So you have n pairs separated by tau. Okay? So these pairs can be either, they can be 1, 1. I'm sorry. Okay, so I'm being, okay, now, select those pairs where the first guy is 1. I'm in a time period where the receptor is occupied. So this is n pairs separated by tau, first entry is 1. All right, so I have 1 1s, I have 1 0s. But I don't have any 0 0s or 0 1s, right? Because I'm insisting that the first guy be a 1. Okay, so I just pick n of those. Okay. Now, okay, of those n, the number where the okay. Okay, so there are going to be n times p average of these guys. All right, because I'm insisting that the first guy be a 1. So I was picking the first guys at random. So and now I want to say that first guy is a 1. He's occupied. So the average occupation probability is the key. That tells me that the number of these guys on average is n, the number of pairs that I chose times p average. Okay. Okay, and so let's see. And the number where the second. Okay, so that's the total number of pairs of this kind. All right, so and now the fraction where the second of these the fraction that are nn are 1, 1. Is just g of tau. All right, that's what g of tau means. It means remember, g of tau is going to, unless both times, the initial time and the time later by tau, correspond to receptor occupied, you get the product of the two occupation numbers is 0. It's only 1 if both of them are 1, okay? So the average, so g of tau is the fraction of these guys where both entries are 1, all right? Okay, so what they now say is, so what happens if we increase tau by delta tau? All right. So, for each of these guys, this is a time and this is the later time by tau. And now I say, okay, well, actually what I'm going to do is to look at the situation when the later time is not separated by tau, but by a little more. okay, by tau plus delta tau. So maybe this 1 became a 0 if I let the second time be a little bit later. All right, there's some of those. Maybe it stayed a 1. There's some of those, okay? And what about these guys? Well, some of these, if I increase the later time by delta tau, will stay 1 zeros. In other words, it won't get, but some of them will turn into 1 1s, okay? So you have to think about that, and what's the fraction of such things? And the idea is to do a census of, okay, so initially the 1 1s were n times g of tau. That's the number of 1 1s in my initial thing. Okay. But I'd like to know now what is the number of 1 1s after I've changed the time interval, the delay time, a little tiny bit. Okay? So of the 1 1s that I had to start with, some of them will stay and some of them will go. Okay? And so I add them all up. And the claim is that if you work it out, think through the g of tau times d tau over tau b. So you're going to lose guys where you had a 1 1, but if you looked at the second guy a little bit later, he had turned into a 0, right? The bound guy went off. And the rate at which that happens is 1 over tau b. So you're going to lose some stuff. And you're also going to gain some stuff due to the receptor wasn't occupied, but it became occupied. All right? And so if you work that out, you get this, n times p bar minus g of tau. So this part is a tad tricky. Times p over 1 minus p. You have to think a little bit to convince yourself that. But anyway, so there's a term where you lose and there's a term where you gain. All right? And you can turn all of this into a differential equation. So this is, you change the time interval and you want to know what is how does the correlation function change? Well, the number of events that you had initially is that, and then you lost some, and then you gained some, and you tried to estimate what the loss rate was and what the gain rate was. So you turn all of this into a differential equation. d tau, in other words, I subtract this from the left-hand side, and you see that I'm calculating a derivative. The overall number of events that I took into consideration, n, is simply a multiplicative factor of everything, all right? So nothing changes if I double it or triple it. So when I'm all done, I've got a differential equation. dg dt d tau is equal to minus 1 over tau b, the off time, times g of tau, plus p bar over 1 minus p bar minus g of tau. This is the, when you're at this stage, you say, how the heck am I ever going to get something simple out of this? 1 over tau b. So, all right, so you do a little bit of probabilistic arguing, and you get a differential equation for this correlation function. Now you just go back to your, now it's calculus. You have a differential equation and you try to solve it. Okay, so I won't go through the guts of that, but you can solve this differential equation. Okay, and the differential equation solution So, all right, so we're messing with pairs. Well, okay, I don't have to rewrite it. Okay, I'm not gonna, you find an integrating factor, you integrate it up, you impose the boundary condition. The boundary condition is that when tau goes to 0, you should get p average. Okay, so there's solve, so here's solve the differential equation. All right, it takes you a good half hour or more to do that correctly, but it's not so hard. And then impose boundary condition. First order differential equations, you have to know one thing. You have to know where it's going or where it starts, okay? So what do you expect? What's a good boundary condition? Well, okay, what does this g of tau mean? It's the correlation between two events in this curve that are very close together, all right? Well, if they're very, 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 very close together, you know, whatever the first one was, the second one will be the same thing. If the first one was 0, the second one will be 0. If the first one was 1, the second one will be 1. And so if you average over all of those, you're just taking the average of the occupation number. Okay, so g of 0 has got to be, that's the boundary condition. And if you mess with that, if you are determined and stick it through to the end, you discover that the solution of this differential equation with that boundary condition is this guy right here. And you know, at this stage, one has no reason to believe that the answer you're going to get in the end for what's the fractional error is something simple or intuitive, okay? So I wanted to take you from, okay, there's some magic to get to this correlation function. And this correlation function looks sort of complicated. But when I put it to work in evaluating the fractional error that the cell is going to make, the answer in the end is, you know, at this stage, okay, the 1 over square root of t looks physically reasonable, but I don't have a direct interpretation. But then when we transformed it into this, we actually got a pretty clear physical interpretation. It's just 1 over, you know, up to factors of order 1, it's just 1 over the square root of the number of binding events that actually took place during your measurement interval. Okay, makes sense, okay? All right, so if you want to go through the argument that gets you to the differential equation, which you can then amuse yourself trying to solve with that boundary condition to get the answer that we used, it's just a page in this Berg and Purcell article, and it's, you know, it's not technically hard. It's just at each stage you have to think, what does it mean, or how do I, you know, what is the correct thing to put down for how many 1-1 events I lost by increasing tau by delta tau, and how many new 1-1 events did I get by increasing tau by delta tau. All right, so I claim that the answer is simple. Well, not so simple, but it's perfectly understandable. See, this guy, p bar minus g of tau, this is the, p bar is all of the 1-1 events. Listen, what do I want to say? This term is counting for you the number of 0-1 events that become 1-1. So this difference actually is the number of 1-0 events, all right? P is all events, G is the 1-1 events, and the difference between the two is the 1-0 events, all right? So this is the 1-0 events. What fraction of them turn into 1-1 because somebody comes on, all right? And to express it in terms of, that has to do with the on rate and the probability that something falling on can actually be absorbed because the site is not occupied. And so, but I express it in terms of the off rate. Well, I just used the, you know, the kinetic steady state argument to connect on rate times 1 minus occupation number with off rate times occupation fraction, right? Okay, anyway, you can do that if you are so inclined. It's kind of remarkable. Okay, so what does this mean? What is this good for? By the way, we could have gone, I could have given you essentially the same argument by saying, I could have gotten to almost the same result by saying, okay, let's imagine we have a magic measuring device that tells you in some volume, some little cube, how many molecules there are, all right? And I know that number is going to fluctuate, okay? So how do I estimate what's the error that I'm going to make in the estimation of what's the number of molecules in that cube? Well, it's going to be square root of n. That's Gaussian sort of thing. And if I make multiple measurements, it's going to be square root of n, 1 over square root of n, right? The question is, how many measurements can I in fact make? Well, if you've measured how many molecules are in your little cube once, and you want to make a better measurement by taking a second shot, you have to wait for the guys that are inside the volume now to have diffused out so that you get an independent look at how many are in the volume. You understand what I'm saying? That is to say, you can increase accuracy by taking more measurements, but the measurements have to be statistically independent, okay? You can't, you make a measurement, your apparatus is set up in some way, and 1 nanosecond later, you make the same measurement. Well, nothing's changed. You're not getting an independent shot at this thing that has variance. And the time that it takes for things to, well, the issue here is you have to get a second independent measurement of the number of molecules that are in this volume. So you have to wait for the ones that are in it at the time you measured to diffuse out and a different set to diffuse in. That's how the diffusion constant gets in the game, and that's how, by waiting a certain time, the number of independent measurements you get is the time you waited divided by the time it takes for stuff to diffuse out and back in, okay? So and if you follow that logic, you'll get to exactly the same argument here. Although this is different. We're not claiming to measure directly the number of molecules in a volume, all right? But which is why we went through this song and dance. We have a receptor. Okay, so let's put in some numbers and see what this tells us. Okay, biological impact of this craziness. All right. So, where did it go? I had an eraser. I hit it. Okay. Okay. So the basic point is that if you put in the numbers, you will see that. Okay. So let's do it. There are kind of two things going on. One is I can say, well, the E. coli has to know in which direction to move in order to get to a better place, right? A better place is where the concentration of something interesting or edible is higher. So he has to measure the gradient, you would say, of the concentration. How does he measure the gradient? Well, he could measure something on the front of the body and something on the back, and if they're different, if it's higher in the front and lower in the back, then that suggests you ought to move towards the front, and vice versa, okay? So if you put in the numbers here, the E. coli cannot do this because the gradients involved, suppose that the gradient is the concentration changes by something of order 1 over, I don't know, a centimeter or something like that. Well, the poor E. coli is only a micron long, so that's 1 in 10,000 of the scale over which the concentration is varying. So it has to be able to make a measurement where the fractional error is small compared to 1 in 10 to the 4. all right? Okay, so putting it, when you put in all the numbers, that would say, yeah, you can do that. You can measure with an accuracy of 1 in 10 to the 4 the fractional concentration, and therefore directly measure the gradient as long as you're willing to wait a year. So this is no good. The poor guy will die before that happens. So he's basically required to do something else. Okay, so let's see. God, back hurts like nobody, doesn't it? Airline travel is very, very bad for your back. Never do it. Okay, so what does the E. coli actually do? Okay, before I go through that, let's put in a number or two to figure out what's happening. All right, so we want to, so our delta C over C, what can, how accurately can he make this measurement? Well, we have a way of we have our estimate, so close enough, square root of D times a size times a concentration times a time. Okay, so what is this DAC? Diffusion constant, dimension, concentration. Well, suppose the concentration is, let's see, what am I going to say? 1 nanomolar, which is not a, maybe that's small, but it's, we know that, in fact, we know that the E. coli can make measurements of, can detect nanomolar concentrations. So this is about 6 times 10 to the 17 per meter cubed, okay. D for, a self-respecting edible molecule, glucose or something like that, is like 10 to the minus 6. 10 to the minus 9 meters squared per second. You can look up these things. And okay, so let's put in a, I don't know, let's put in a size of order 1 micron. All right, so this number then turns out to be 600 per second. And therefore, if you take time to be 1 second, so this goes to something like 1 over 30 for t equals 1 second. And the exact number you're going to get out, the actual fractional accuracy will of course depend upon the time. Probably we should restrict our attention to times of order second, because if you actually watch these guys doing their thing under the microscope, you can see that they do things systematically for seconds at a time. And basically, there's various reasons why this is the right time scale to talk about. The diffusion constants for the things of interest don't vary all that much. The thing that might vary is how, what we put in for this number. The fact that there's a square root involved means that it doesn't depend all that much on this. So this number, it's order percents. So roughly speaking, under reasonable conditions, this delta C over C is percentage. And so what I said was, under any reasonable scenario, 1% is just too gross, too poor a measurement to be able to directly detect what's the gradient of something of interest across the body. So what does the E. coli actually do? It does a thing called run and tumble, all right? So and we can understand why that works. So when you actually see, you watch what's going on under the microscope, you see that the trajectory of the bacterium is something like, it runs in a particular direction for second-ish. And then it kind of fiddles around and chooses a different direction. Again, second-ish, chooses a different direction. So it undergoes a random walk, all right, but it's not a thermal random walk. What's happening? So the E. coli guy has flagelli, plural, multiple ones. And these are long molecules that have a screw sense. And you know, they're all left-handed screws or something like that. And there's a motor connecting this flagellum to the body, and the motor turns, right? It makes use of potential difference, electrostatic potential difference, to run the motor. Now, the motor can either run clockwise or counterclockwise. And when it's running counterclockwise, the flagellae are all doing the same thing. They kind of wrap themselves around each other, and they make a kind of screw propeller that causes the guy to move forward. So this is, if these guys are going counterclockwise, looking at it from the inside, the fellow moves forward. However, this motor never runs in the same sense forever, right? It does it's counterclockwise for some fraction of the time and clockwise for 1 minus that fraction of the time. And when it's clockwise, when the motor is running clockwise, then basically all of these flagellae get disordered, and the bacterium doesn't go anywhere. It sort of tumbles. And then when the motors all turn to being counterclockwise again, then it goes back to this state, and it's running smoothly forward. It's being propelled, but it's in a new direction. It's kind of randomly chosen. So how does this help? Well, the idea is that as you're running, if you're discovering that the concentration of the thing you're interested in is increasing, that's a sign that you should keep going in that direction. If the thing that you're measuring is decreasing, then you're going in the wrong direction, so change direction at random, since you don't know which direction to go. This is a so-called biased random walk, and it's a strategy that really works. Now, all you have to do is to convince yourself that if this guy runs for a second, he can measure the change in concentration accurately enough between here and here so that he can detect the gradient, right? So this is now a much easier problem, because if I have to simply be able to reliably detect that the concentration is smaller here than it is here, okay, the actual fractional change in the concentration is much bigger than what we were talking about before. So suppose the natural scale for variation of the concentration is a centimeter. All right, I now don't have to detect that over 1 micron, but I have to detect it over however far the bacterium can move in, let's say, 1 second, okay? So let's see, I have some numbers on that. Yeah, so supposing that the scale for variation of the concentration of the thing that's of interest is lambda, and suppose lambda is a centimeter or something like that, maybe 10 centimeters, who knows? You know, you put, there's some localized source of nutrition, but it's not, the scales of these things tend to be macroscopic, right? I have a decaying animal over here, and I'm over here, and I've got to move up the gradient. Well, we're talking about it, let's say centimeters. Okay, so, and in my time over which I'm making the measurement, I'm moving at some velocity, then, you know, the fractional error that I have to be able to detect is how far I can go in this time divided by the scale over which the concentration is actually varying. Okay, so so this is the fraction that I've got to be able to measure And this has got to be bigger, I guess, than this problem, right? The thing that is, so what we decided was that this is going to be 1 over square root of dAct. So we said for, reasonable numbers, this guy could be of order 1%, all right? So the real question is, and these times have to be of order seconds, all right? So the real question is, does this inequality hold? If it does, we're golden. That is to say, the guy can actually detect with sufficient accuracy the change in concentration over the stretch that he's going to be going in one direction, okay? So the only real question is what's V? So what did I say? V tends to be hundreds of microns per second. So 100 microns is 1/100th of a centimeter. So, if the velocity is hundreds of microns per second, okay, so this is a number that has come out of nowhere, right? It's just a number. It's what you observe, okay? And okay, we could go back and understand how is it possible for a guy with flagella that have a certain dimension, da 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 da. Okay, we could work it out. And that's not uninteresting, but observation is this. These guys move for the 100, in a second they can move 100 times their body length, all right? And so this number is about 1%, roughly speaking, for times that are of order a second. And we already went through the argument that this number, the error, the inescapable statistical error in measuring the concentration is also of order 1%. So it's consistent. This can work, all right? All right, so, and if this number had been different, if the diffusion constants are too small, et cetera, the concentrations are too small, then I'm in trouble. But for situations that actually describe how E. coli live, this kind of inequality seems to be satisfied, all right? And all right, so anyway, this is why the actual lifestyle of the bacterium is, so to say, consistent with and sort of driven by the fact that measurement of concentration is subject to certain statistical limitations, which we can quantify, have done, and we've seen that, okay, good. It's all consistent. What we see the E. coli do is not inconsistent with the laws of nature, all right, or the laws of statistics. Okay, so the last thing that I want to talk about, in brief, I guess, is going to be, okay, so the idea is that this all works because somehow the E. coli has a machinery that causes the direction of rotation of the flagella to change randomly from clockwise to counterclockwise, and that somehow that's modulated by what it knows, what it can detect about the concentration of the interesting molecules in the solution around it. And so there's a whole story, which maybe I can just very, very briefly describe, and maybe I want to use this guy. Oh yeah, all right. I've got to put the magic finger on, and now what do I do? Oh, there it is. Okay, good. All right, shall we go like so? Come on, you. All right, use that. Okay, just advance it one if you can manage. Ah! All right. Nothing is ever simple. Okay, God damn it. Yeah, there we go. Okay, good, stay there. Okay, all right. So, okay, so once this was all understood, then it became interesting to try to figure out, well, okay, the cell is a collection of proteins. We know that there's a whole class of proteins that are surface receptors, and is there some scheme that we could imagine in which this lifestyle that we've just described can be realized, all right? And so, do we, okay. That's what this is all about. Now, I have trouble keeping all of the players straight in my mind, so don't be upset if after I've talked about this for 5 minutes, you still don't know what the hell is going on, okay? However, it introduces an aspect of, you know, chemical biology, which is really, really, really important and shows up in different forms all over cellular life. Okay, so what we have here, folks, is on the one hand, so up on the left, we have the receptor, all right? This is the guy that is going to either be empty or be occupied by a molecule of interest. It sends okay, and it is connected to some internal apparatus, a protein. And basically, that internal apparatus can be itself in one of two states. It can be active or not active. And it just switches back and forth between active and not active. And the rate at which it switches back and forth between these two states. I mean, that's the great thing about proteins are machines. We think of them first as just three-dimensional structures, but what's really important about them is that these three-dimensional structures they're mutable. And when they are in different shapes, as it were, different states of being, they can carry out other activities. They can be enzymes. They can cause other reactions to occur. So this internal part, which is called key A, can be either in its unactivated state or in an activated state. When it's activated, what is it doing? Well, then there's another protein that's lurking about in the cell that can be, phosphorylated. That is to say, have a, what do you call a PO3 group? Anyway, a phosphate group added to it, which changes its state, all right? So there's this thing called key Y, which can be activated, or can be phosphorylated by the key A guy inside the cell, and when key Y is phosphorylated, it's still something that's free to move in the cell. And where does it go? It goes to the motor. And a phosphorylated key Y changes, when it finds the motor, it changes the probability with which the motor switches from going counterclockwise to clockwise and vice versa. So the whole story is that the receptor, so this is a chemical scheme that causes, yes, and right. So what happens when the receptor actually binds something? Even if it's not binding something, it is flipping back and forth between being activated or not activated and causing the motor to flip back and forth between clockwise and counterclockwise. You want that flipping back and forth between clockwise and counterclockwise to be modulated by the binding of an interesting molecule to the receptor. So when the receptor is bound, I guess that's the bottom pair here, the frequency with which the activation of the internal part occurs is changed. It's less frequently activated when the receptor binds something. And that means it's less frequent for the key Y to be phosphorylated, and that means it's less frequent for it's less frequent for the motor to switch its direction of flipping, all right? Now that's, okay, I think you can see that rather tortured chain of logic says that if I'm binding stuff, then the motor is going to be less likely to change its direction of rotation, okay? And I'm most likely to be moving forward, all right? Now, so that's in rough outline the internal chemical logic that causes binding of, the measurement of the fact that the concentration increases causes the rate at which the motor switches its direction of rotation to decrease, and that means that makes it run in the same direction longer. That almost is the whole story, okay? However, something that's quite critical is called adaptation. Okay, so when you first walk into a room which is very, very bright, the sun is shining directly through the windows, your ability to discern details visually goes away. And after a few seconds, something happens. The responsiveness of your retinal system changes, and so to say, adapts to the fact that the mean level of illumination is high, and what you're always interested in is what's the variation about the mean. So if the mean is high, you want to choose things so that you're sensitive to fractional changes about a high mean. If the mean is low, you want your system to be sensitive to fractional changes about the low mean. That's called adaptation. And all sensory systems in all animals manifest adaptation. And the manifestation of adaptation here in this guy is that, if you've found nirvana, right, you've gotten to the place where the concentration is high, you don't want to upset the apple cart. You don't want to change the rate at which you're randomly walking around. But should it matter whether nirvana is very rich in glucose or only 1/10 as rich in glucose? You want to relax back or adapt to a regime of flipping back and forth between clockwise and counterclockwise that's the same no matter what the constant level is. So that's called adaptation, and up on the upper right, what is being plotted is the rate at which the motor is, or the fraction of the time that the motor is running counterclockwise. And that little blip is the experimenter just inserted a kind of short time, fraction of a second blast of an attractant, okay? And so the rate of counterclockwise motion, the fraction of the time it's counterclockwise, went up, but this pulse of nutrient went away. And so it relaxed back to something. But it relaxes back to a constant that, in fact, is universal. All right, so that's called adaptation. So how you get adaptation out of this system is not so clear. All right, so there's another element. How do you make the adaptation robust? Okay, so there's a story there that I actually probably will tell you about it in outline at the beginning of the next lecture. So the next lecture is going to be about accuracy of copying, accuracy of choice. And when you copy DNA, you may make mistakes. It's very important that the frequency of mistakes be small. Putting the right base in a growing chain of DNA, the fact that you put the right base in has to do with the right base having a stronger binding energy to the thing that's growing than the wrong base. But the actual, the difference between these two binding energies is some finite number that we can estimate, and Boltzmann will tell us what's the probability that you make the mistake rather than putting in the right thing. And that probability is very high. I mean, it's small, but it is it's larger by factors of 10,000 or more than the actual rate of making mistakes in copying DNA or of fabricating a protein from an RNA message and so on. And there's a profound question. How does biology manage to do this? And in order to examine that, we're going to talk about chains of chemical reactions, enzymatic reactions that are kind of like, they're not unrelated in their general structure to this business of what's the chemical activation chain that that makes it possible for the E. coli bacterium to find its food, etc. Okay, so I think it's worthwhile going to the next step here and explaining how adaptation arises, just so we get kind of an entry into the world of chemical kinetics in the biological context, okay? All right, so this was fairly heavy duty from the point of view of equations, and it'll be possibly worse tomorrow, I don't know. But there's a simple idea behind it all, and I'll try to bring out the idea. Okay, thank you.